Hello everyone. Hello everyone. This is Masaka. Welcome to 2021 Summer Paper Virtual Meetup. In this meetup, we met twice a week to discuss papers about distributed systems. In this first installation of the Summer Paper Virtual Meetup, we'll discuss papers from industries like MapReduce, GFS, Facebook's Tau, or Amazon Dynamo. You can always check out our schedule in this website, or you can contact me via WeChat. And the rest of the video is my short introduction of this week's paper. So today we will be covering a paper titled Kakfa, a distributed messaging system for log processing. And the first author of this paper is named Jay Krebs. If you don't know him, he was an engineer at LinkedIn, and later he co-founded a company called Confluent, and where he worked on Apache Kafka for most of the time. So before we start talking about this paper, I just want to give you some background knowledge. So what is a distributed messaging system? A messaging system really defines just two roles: a producer and a consumer. The producer can send network message containing a timestamp event. You can think of an event as a key value pair, and the consumer can fetch it or pull it. And usually there is a third layer called a middleware between producer and the consumer. And we call this middleware a broker or message broker. And the broker can queue the messages and notify the consumer to pull those messages. The broker itself can be distributed and fault tolerance. So the contribution of Kafka on messaging system is that it defines the broker to be a stateless service that relies on append-only log to persist messages. And the log itself is partitioned to multiple shards in order to increase throughput. And I think this system is a very simple design that tries to maximize the near real-time messaging throughput. So why would anyone use Kafka? Like, what's the difference between using Kafka and a relational database? Kafka is particularly useful for processing log data. And you can think of log data as like user interactions. For example, if you go to Amazon.com, you can do a search query or you click some buttons, and those are recorded as events sent to Kafka. The other part are those non-user interactions, such as operational log. So think about like CPU metrics or service arrows, service logs. And those logs are fed into Kafka as well as an input. The output of Kafka are those consumers, and they can use those logs to do analytical work like ad targeting and reporting. You can think about it as Google Analytics, how it's being done. Oh, by the way, I think ads is a particular business area where you need exactly one semantics. This basically means that if a message sends to the consumer can receive it once and only once. If you don't have exactly one semantics, it means that you will either overcharge the ad providers or the company will lose money. And the other useful features are like search relevance, newsfeed, and recommender systems. I want to pay attention to chapter or section 3.2, distributed coordination, where the authors talked about how they partition the log in Kafka. So to give you some basic concept, a topic is a type for a stream of messages. And under a topic, the log can be partitioned to multiple parts. The system wants the number of partitions to be significantly bigger than the number of consumers. And each partition is assigned to only one consumer. So if you are a math person, you can think of as a surjective mapping. Kafka uses Zookeeper as a third dependency to manage membership and metadata. things like broker registry, consumer registry, ownership, and offset registry. It also uses Zookeeper for failure detection, recovery, and partition rebalancing. So I think the rebalancing algorithm, which described in paper called algorithm 1, is the most interesting part. The algorithm itself is deterministic, meaning that if multiple consumers run the algorithm, they will produce the same output. The algorithm is fair, meaning that it evenly spread out the partitions to consumers. It has the minimum cost in terms of data moving because it assigns the whole partition to a new consumer instead of moving or shuffling the data around. But I think it will hurt availability because it's a blocking algorithm. If, say, a consumer crashes during rebalancing, it will cause other consumers to wait until Zookeeper does something else. So I have drawn a picture here to illustrate this whole setup. So the motivation for Kafka is a distributed log. Although I only draw one log here, but you can think of this log as partition to multiple machines. And it takes producer as like your mobile phone or web front end. And those producers directly append to the last entry of the log. And there are underlying systems like a database or a caching layer or a search index or monitoring service. They consume this log and do some analytical work, either online or offline. So they can be running MapReduce, or they can do some like online services. There are a lot of concepts in Kafka, like a topic or broker, consumer groups, partition, consumers. I don't think you need to worry about it, but the most important thing you need to know is each consumer owns multiple partitions, and each partition can be owned by only one consumer. So in this case, we have a consumer group subscribing to topic A and B. And inside of the consumer group, we have C1, which stands for consumer one. It subscribes to P1 and P2 in topic A and subscribe to P1 in topic B. And that's what I think is important to know. And there is also a Zookeeper living in the cloud as a external dependency to manage those metadata. So for example, how does P1 knows it's being owned by C1? How does broker know it has P1, P2, and P1 and P2? How does topic A knows P1, P2, P3 owns by topic A? So those information are kept in Zookeeper. All right, so let's briefly go over the rebalancing algorithm. Suppose we have this following simple setup. We have one consumer group from C1 to C5, and we have one topic A being subscribed to this consumer group. And inside of it has 10 partitions, P1 to P10. Now, suppose we add a new consumer 6 into this consumer group. So adding a new consumer triggers the rebalance algorithm for each of the consumer. Now we just call it CI, as using I from 1 to 6 as an index. And the algorithm goes for each topic in CI, we first remove the ownership. And by removing the ownership, we basically blocks the consumer from consuming the logs anymore. And after remove ownerships, for example, if this is C1, we just cut these 2 arrows, and P1 and P2 now no longer belong to C1. And we try to get the set of partitions and consumers, and we sort them based on index. And this makes the algorithm deterministic. So the set of partitions are going to be P1 to P10, and consumer set is going to be C1 to C6. And next, we are going to get a ratio between the number of partition over the number of consumers. And in this case, it's going to be 10 divided by 6, which is 5/3. And we reassign those partitions to CI based on this formula. I times 5 over 3 to I plus 1 times 5 over 3 minus 1. And after that, we declare these partitions owned by this consumer and invoke polling. And at this stage is when the consumer starts working. So think about if the consumer breaks or crashes in the middle of this rebalancing algorithm, and the other consumers try to get ownership of this specific consumer, will be blocked until Zookeeper figures out this consumer is down and they need to do something about it. And that's why I think this algorithm is a blocking algorithm. So at the end of the day, the output of the rebalancing algorithm is going to be like this. C1 now owns P1 instead of P1 and P2. And C6, which is the new consumer, owns P9 and P10. And notice that there's no data shuffling, and this is just a reassignment of the partitions. And the partition number is being fixed. And I think that's important to know. You cannot change the number of partitions in a topic once it's being created. Okay, all right. So the overall downsides of this paper, I think there are 3 points. The biggest one is there is no replication being mentioned in this paper. At the time when the paper is written, the messages are not durable because they are not replicated. Although they are written to a log, which it's a disk, but if the disk is down, then the messages are lost. I can think about 2 cases the data can be lost. The first case is when the producer sends an asynchronous message to the broker, and the message in the middle of the transmitting is being dropped and never lands in the broker. Then the producer doesn't know this, and there is no retry mechanism. So this message is lost. And the second point is before the broker flushes cache message to disk, it crashes. And all of those messages in the cache will be gone, and there is no way to recover them. And building on top of the first point, the system doesn't guarantee the consumer will receive a particular message. I assume it uses a ring buffer because otherwise, if the log grows too big, bigger than what the node can handle, bigger than the disk, it will cause some problems, right? So I assume it uses ring buffer to override the first index once the log reaches maximum. And if it uses ring buffer, then when producer sends more messages than what consumer can pull, the old unconsumed message will be overwritten by new ones, hence violating the at least once semantics. Even though the producer sends the normal rate of messages, there can be like straggler consumer, which caused by like internal frictions or errors. The consumer is just too slow. This can also affect how one partition is being consumed because each partition belongs to exactly one consumer. And at the time of the paper was written, there is no window-based near real-time stream processing, and there is no support for rich data type. And I believe that's my take on the 3 downsides of this paper.